Welcome, students. So this is just a replay of our very first lesson on Unit 3. Unit 3, the topic of the atom. You can see here that when they passed out artistic talent, I ended up with 0 or -2. But anyway, what I hope to happen is I hope to be able to jar your memory about things that you probably should have seen in your past. And then we'll begin to build from that a little bit of momentum about some new learning. So let's get underway with taking a look at the new unit. The unit actually has a title. The title we're going to call it Unit 3, Atomic Structure and the Development of Atomic Theory. We got some very specific goals in mind for today's lesson. So let me share with you what that is. So let's make this maybe just a little bit larger for you. Okay, so like I said a moment ago, our goals for this lesson are to just kind of speak about the structure of the atom, which I think many of you will recall that you've seen before, and then develop a little bit of a historical perspective about how we know some of the things that we actually know about atoms. How do we come to those beliefs? And we're going to find out that most of the information that we are working with in terms of our beliefs are based on a type of evidence called indirect evidence, which is a little odd. So we'll be taking a look at kind of what that means throughout the course of history. Not a complete course of history, but to give you appreciation. So today's lesson has some very specific goals in mind, and these 4 goals are what I have in mind. First thing, we ought to be able to identify the 3 subatomic particles. That should ring a bell. Our protons, our neutrons, our electrons. Those are our 3 subatomic particles. What is their relative location? Where are they found in an atom? Where do they live or reside? The charge, the relative charge, how do we compare our charges? Some of those particles have charges, right? One of them does not. And if we were to compare how heavy one is to the other, how would the relative masses compare? Next thing, describe the relative size of the nucleus of the atom compared to the rest of the atom. Some key terms after that: atomic number, mass number, isotope, very critical words to understanding in this unit. And then describe how an atom can inherit what we call net charge. Atoms are supposed to be neutral, have no charge, 0. So we want to see, well, how does an atom inherit a charge? And then it's actually no longer called an atom. It's called something called an ion. So we want to see how that net charge develops. What's the root cause of that? All right, so let's get underway. So what you might recognize here, something similar to the Jimmy Neutron trailer for the cartoon, Jimmy Neutron. We're going to see that our protons, our neutrons, and our electrons are arranged in a very specific way. So our protons represented by the little red sphere on this model, the blue sphere on this model looks like they're found in a certain spot. Our neutrons also found in a certain spot, and our electrons found differently located than, or located differently than our protons or neutrons. So let's briefly speak about that. In the nucleus, right, in the nucleus of the atom, that's where our protons are located. So our neutrons also located in that nucleus. So the nucleus is made up of the protons and the neutrons. The story changes when we speak about the electrons. They're found on what we call energy levels. Some people like to call them shells. As we progress in time together, we'll use various language that kind of describes relative location of them. And what we know or believe about them is they whiz around the nucleus in what we call energy levels. So they're not part of the nucleus. If we were to compare the relative mass, the mass of a proton and a neutron are identical. Not quite identical, but we say they are relatively identical. We give them a mass of 1 atomic mass unit, AMU. So it turns out they're not exactly 1, right? One is a little bit heavier than the other, but for all intents and purposes, for the work that we're doing right now, we can say that they virtually have the same mass. Story changes when we look at the electron. The electron is fractional value, almost like 2,000th of the mass of a proton or an electron. So we like to say the electron has a mass that is negligible. If you ever heard the term negligent, the word negligent kind of means that somebody has not paid attention to some detail that they probably should have been paying attention to. So when we say negligible, we kind of say we don't pay attention to the mass of an electron, because it's so much less than the mass of a proton or a neutron. It's like comparing pennies to dollars. right? Pennies are negligible compared to dollars. They seem far less significant. Okay, so our basic structure of the atom, hopefully this was a review for most. The relative size of the nucleus of the atom. The nucleus is actually important because when we go back and we think about what we just said, the nucleus is where all the mass of the atom is. The protons and the neutrons are packed in there. However, what we come to learn is that most of the atom is made up of empty space, and the nucleus is really, really tiny. So the nucleus contains all the mass, but it's like the smallest part of the atom, which is a little bit odd. So here's a nice analogy for that. If we were to take a marble, take that marble and place it down in the eagle's eye, down at the 50-yard line at the link, the nucleus might be represented by the marble. The rest of the stadium would be all of that empty space where the electrons whiz around. So the relative size of the nucleus, even though that's where all the mass of the atom is packed into, it's actually the smallest part of the atom. Most of the atom is what we call empty space. So some very critical words to developing key understanding in this unit. First one's called atomic number. If you look at a standard version of any periodic table, you're going to see atomic number in most versions of any periodic table. So here's one from a textbook, right? We got lots of numbers on there. So if I were to point my finger at a specific element, let me pick an element that maybe we're familiar with, hydrogen, right? The number 1, right? The atomic number 1 represents hydrogen. What it is, it's the number of protons in an atom. It's found on every periodic table. It's always a whole number, and it identifies what an element is. For example, helium has atomic number 2. No other element can have 2 protons, exactly 2. So only helium atoms have exactly 2. Compare that to oxygen atoms. All oxygen atoms, atoms have exactly 8. So atomic number, it's the identity of an element. It's specifically the exact number of protons in an atom. Key term called isotopes. Turns out that atoms of the same element are not identical in every way. So what we've come to learn is that the number of neutrons in atoms of the same element may vary. And we call those atoms that have different numbers of neutrons, we call them isotopes of the same element, So carbon-12 and carbon-13, they're both carbon, right? They both have the same number of protons. For carbon, it turns out to be 6. Well, carbon-13 has an extra neutron, so it's a little bit heavier. So if we were to look at this, right, both carbon, 6 protons, 6 neutrons, that's carbon-12, right? Carbon-13, 6 protons, 7 neutrons. Carbon-13, not a coincidence. 6 plus 7 is 13. 6 plus 6 is 12. So this number back here is critical to identifying what type of carbon we're talking about or which isotope. Mass number. Mass number is this number that follows carbon, carbon-12, carbon-13, and all that is, it is a sum total of what the nucleus is made of. 6 protons and 6 neutrons, we call it carbon-12. 6 protons but 7 neutrons, we call it carbon-13. They're both carbon, one's heavier than the other. So the mass number includes the total count of everything in the nucleus, right? The protons and the neutrons. Key terms to understanding in this unit. These 3 words are super critical, and your first assignment will help you kind of wrestle with this idea. You got to wrestle with the ideas to understand. So my goal for the first assignment in this unit is to have you wrestle with those words in various ways, actually visual ways, to develop deeper understanding of them. So here we can kind of take a look at ways that we speak about isotopes or represent them. So those key words that we just talked about, mass number and atomic number, appear here now in special symbols that we call isotope notation. And it represents the structure of different kinds of atoms of the same element, isotopes. So the isotopes that we're looking at specifically on this are all isotopes of lithium. Oddly enough, isotopes of an element, they're a little different by how heavy they are, but they chemically behave in the same way. And that allows scientists to do interesting things with them, which we may talk about at another time. So most naturally occurring elements, right, not man-made elements, the naturally occurring elements, have various isotopes that they may exist as. So for example, lithium has 3 of them. Lithium-6, lithium-7, lithium-8. They're all lithium. They all have atomic number 3. 3, 3, 3. What is different is their mass number, 6, 7, 8. So that lets us understand the structure of these 3 lithium atoms, what they're made up of, what are their parts. So lithium-6, right, it's lithium. We go to the periodic table, right, we find lithium, right? Lithium on the periodic table, at least in this book, is highlighted in a gray color. So if I were to zoom in on that, right, look at lithium has atomic number of 3, Li, right, atomic number 3. So that means 3 protons. So this guy shows 3 protons for each of these atoms. The atomic number is 3. Well, what would be the mass number of lithium-6? Well, we just count all the parts in the nucleus. 1, 2, 3, 4, 5, 6, right? How many of them are protons? Well, 3 of them. How many of them are neutrons? Also 3 of them. And now for electrons, we look outside the nucleus, right? Those electrons whiz around the nucleus in what we call energy levels. So they're the red dots. So when we speak about atoms, atoms don't have a charge. Atoms are electrically neutral. So the positive charges and the negative charges always add up to 0 if we're speaking about an atom. There are situations where we don't speak about atoms. We speak about specially charged particles called ions. And then this fact changes. And that's going to happen in today's lesson. So for now, we're assuming that we're comparing atoms that are neutral. Atoms, we assume, are electrically neutral. So the proton and electron count should be identical unless we have information to tell us otherwise. Okay, so lithium-7, right? Again, it's lithium. Atomic number has to be 3. Mass number now, total parts in the nucleus. Looks like there's 7 now. 3 of them are protons, right? 4 of them are neutrons. It's an electrically neutral atom, right? We're talking about atoms here. Still, no, we're not speaking about these things called ions yet. Ions have charges. So our protons and electrons need be identical. Lithium-8, right? Still lithium, atomic number 3. Mass number is now 8. Now I count the total parts in the nucleus, lithium-8. Let's see, there's 3 protons, 5 neutrons, right? So 3 protons, 5 neutrons. Well, it's still a neutral atom of lithium, so we're going to say the electron count is still 3. So this is how we rehearse speaking about these key words. Isotopes, atoms of the same element, different numbers of neutrons. Mass number, right? Total parts in the nucleus. Notice when they write these isotope symbols, mass number is always on the top, right? Atomic number is always on the bottom. The mass number tells us that this is a different isotope of lithium than these 2 over here to the right. Now, one thing that can happen, and this is the last point in today's lesson, is that sometimes atoms will look to become more stable, and they can do that a number of ways. One way would be to either gain electrons or lose electrons, and that's a behavior that some atoms undergo. So an atom's typically thought to be electrically neutral, and this means that for any atom, the protons and electrons are always the same when we speak about atoms, but what may happen is either electrons could be lost or electrons could be gained, and then we're speaking about something that has a net charge, something that we call an ion. And usually the reason that atoms form ions is to become more stable. So in most cases, the ion version of the atom is stable when it forms naturally. So what we're looking at is comparing the proton count to the electron count. Over here on the left, this model, if we were to count the protons in the nucleus, well, it says it's sodium, so it didn't really show it in the model. It just showed us this red dot for the nucleus. But if we were to get our periodic table out and look up the element sodium right here, right, Na, right, sodium has atomic number 11, which means it has 11 protons. Count the little blue dots, right? Well, the little blue dot says it has 11 electrons. That's because atoms are supposed to be electrically neutral. So a sodium atom has no net charge. The plus amount and the minus amount, let's activate a little pen here. All right, so our plus amount and our minus amount add up to 0. There's 11 positives, so that's like adding up plus 11 and negative 11. The sum of plus 11 and negative 11 is 0, net charge, none, right? Counter to that over here, now they're talking about a sodium ion, sodium that has a charge now. So now we add up the pluses and, well, look, it lost one of these blue dots. So now the model only has 10 electrons. So now there's minus 10 compared to plus 11. Remember, the pluses are the protons, the minuses are the electrons. So there's 10 electrons, but 11 protons. So now that has a net charge. The protons outnumber the electrons by 1. So its plus charge is plus 1. So sodium has a net charge of plus 1 as an ion. Now, how did we know that it lost 1 electron, or how did we know that that's what it would do? That will come later in this course. But for now, I'd like you to recognize comparing proton to electron count. Okay, so let's clear this up. And let's just take a look at a few examples. So like I mentioned before, if we're going to determine the net charge of an ion that forms from an atom, we compare the protons and the electrons. And if there's more protons, it has a charge related to exactly how many more. If there's more electrons, it has a charge related to exactly how many more. And we recall neutrons don't matter, right? Net charge 0. We don't care how many neutrons it has because it doesn't change the charge of the atom in any way. So let's put that into practice. So there's a little legend here. We're going to take a look at a couple quickie models. The red dots will be the protons, right? The large blue dots will be the neutrons, and the tiny little black dots will be the electrons. Remember, electrons barely have any mass, so we represent them as smaller dots here. So here's a little table, right? And I kind of redlined neutrons. We're not going to worry about neutrons because they don't matter for net charge. So we have a model. We're going to count the parts in the model. Well, 2 of them are protons, 2 red dots. 2 of them are electrons. 2 of them are neutrons, but we don't care about the neutrons. So we compare the count of the pluses and the minuses. When we do that in this example, right, we see that we're comparing 2 positive, or plus 2, to 2 negative, negative 2. And if I add that up, plus 2 and negative 2, right, lo and behold, that adds up to net charge of 0, no charge. Let's do it again for another model. Oh, look at this. We stripped away the electrons. So you can actually have an atom that doesn't have electrons, right? So it's no longer called an atom then. Now it's called an ion because it has a net charge. So we still have 2 protons, we still have a nucleus, but we have 0 electrons. So now what we think about is, well, look what happened here. So here's what happened. Now we're comparing plus 2 to 0. Well, aren't there more protons than there are electrons? If there are more protons, it has a plus charge related to exactly how many more? Well, it has a plus charge of plus 2 then, right? Again, we ignore the neutrons. One final model, right? Let's interpret what the model tells us. 1 proton, 2 electrons, 2 neutrons. Remember, electrons are on the rings here, right? There's 2 of them. We don't care about the neutrons. So now what we're thinking about in this guy is we are thinking about the case that there's 1 positive, but 2 negative, right? The negatives outweigh the positives by 1. So here is our statement. If there are more electrons, which there are 2, it has a charge, a minus charge related to exactly how many more. There's 1 more, so it inherits a charge of minus 1. And this is how we kind of think about comparing the parts to determine an overall net charge. So that concurs the first lesson in our unit on atomic structure. And I hope that you find this useful for reviewing, if need be, for preparation for the first assignment in this unit. So until the next time, folks, remember to respect your chemistry, but don't fear it. I'll talk to you soon.